That's fine. Review naman yung first part. Eh. Anyway, the reason we choose quiescent point A over quiescent point B is the fact that A has gain. If we were to operate the thing, no? If you remember, this is a voltage amplifier if we interpret it like that, right? Kasi ang output natin is voltage, ang input natin is voltage, no? It's a voltage amplifier. So, the reason we choose A is because there is a lot of gain on A, right? But in B, there is very little gain because if we shake, no? If we put a small signal value around V in, no? So we put a small signal V in here, we're going to get nothing, really. We're going to get no output kasi hindi nagbabago from 0.2, no? So we don't want to be in B, all right? Next. So then, why would we choose A over C? This is the thing that I was talking about near the end of the last lecture, no? Which is that if you're in A, your output voltage can swing all this way. Kaso, when you're at C, your output voltage can only swing this much if it's centered at C, right? So, if you're going to make an amplifier, then you'd like one that can give at most the maximum, like the biggest output waveform possible because that's what an amplifier does, right? Doesn't matter if C has a better gain, no? If it can't make as large a wave of an in the output as A does, then you don't want C either, no? So that's what goes into choosing our quiescent points, no? So A gives us high swing, no? All right. So let's take that and let's redraw the same circuit with the example values. I'm pretty sure these are the same example values as we had in the lecture last Wednesday. It's 1K, 5 volts, then K, and then we have a small signal V in. And then we have a large signal V in. And so if you guys remember, no, this one is constant. It's a DC. This one is a very small value, but it's a as an AC value. It's an oscillating value. No, so that's your small signal, and your total V in would be small letter with big letter, which is equal to big letter with big letter plus small letter with small letter. Diba? So that's your total input. Yes. Which leads to a V out, no? So we have a biasing, no? So ito ulit yung transfer characteristic. And they tell us that this is 0.94. And he also no? So then, since the DC voltage no for the input is 0.94, then we can place the quiescent point here, no? At 0.94. No? So solving for so this is V in and V out, right? That's your transfer characteristic. So given that 0.94 volts V in, let's solve for V out. We have 5 minus 1K times beta, no, which is 100, no? So let's just note that down here. 100 times 0.94. Well, sige. 100 IB na lang muna. No? And then IB is equal to 0.94 minus 0.7 over 10K. No? Which puts it at around 24. Yes, 24. But it's actually 0.24 over 10K would be 0.0024K. Over K pala, no? So this becomes 0.0024 milli or 2.4 micro. So that's IB. And then V out would then be 100 times this thing. No? So that's 5 minus 1K times 240 microamps. K times micro would be milli. Biglang, there's something wrong with our math here probably. Sige, let me just pull out a calculator na.
I'm also trying to do that. It's because for Kim, he will be difficult and just but not that I'm doing myself, but I'm doing
4.976 ang output natin here, actually. So then this would be our quiescent point for this case. Wait lang there seems to be something wrong with this. Iba yung sinasabi ng slide.
I'm not sure.
Sige, let's just put that aside for now, no? Kasi ang nakuha nating sagot is 4.976, di ba? So, we'll keep it at that, no?
But was it 0 precise for that? That's why I don't want something. Because it will only be good. It can only be good for us to do high standards of requirements for that. So I still want to think the
Okay. So,
but
ayun na, 2.6. Mali lang yung pagkakalagay ko sa calculator. Anyway, 2.6 ang lalabas dito. No? So, V out is equal to 2.6. No? So, with that, we get a quiescent point for this circuit. And note na, sige, let's review what we did. No? What we did was basically to turn off the small signal portion. No? We turned off the small signal portion and did DC analysis to place us on some operating point A, no? Where A, in this case, was the operating point where we had 0.94 as the V in and the V out is 2.6 volts. No? Specifically where one where the IC was found to be 2.4 milliamps. No? So what we tend to want most of all when we're calculating the quiescent point, no, for a specific biasing is IC, no, because IC is what we use to determine the small signal gain. So that I, right? So then let's talk about the load line. So the quiescent point actually, the circuit rather, no, outside the BJT, someone in WFY actually asked a question about this back on Wednesday, no, where um I don't remember the exact question, but his question had something to do with the BJT output characteristic, no? So let's remember what the BJT output characteristic is. The output characteristic is IC versus VCE, no? That's the BJT output characteristic. Meron tayong mga curves na ganito. Diyan, di ba? Yan. So this is the BJT's output characteristic, di ba? So I hope you guys remember, no? Na parang ang output characteristic ng BJT is the currents start to fall after VCE sat, which is at around 0.2 volts, di ba? So ganun yung itsura ng output characteristic ng BJT. Additionally, these lines, no, they point towards something very far into the negatives, which is the early voltage, no? But that's going to be important later on pa naman, no? Anyway, what we have here is the fact that, no, given VCC, RC and RB, no, um dito sa circuit natin, 'di ba may load line 'yan? Depende sa VCE natin, no? Depende sa VCE natin, itong output load has a load line. Meron siyang, so at IC equals 0, 'di ba? At IC equals 0, VCE would be VCC, 'di ba? So that's one of the points dun sa load line natin. At VCE equals 0 naman, IC, no, is equal to VCC over RC. Diba? Kasi VCC minus 0 over RC na yun. No? So at VCE equals 0, VCC over RC na to. At IC equals 0, VCE equals VCC dito sa baba. Diba? And we know that these two are related by a resistor. No? So linear yan. No? So in this case, nakikita nyo visually, no, yung possible quiescent points nung circuit, no? Kasi ang ma-allow lang na quiescent points really is the quiescent points that are allowed by the resistor, no, by the load line and by the BJT output characteristics, no? So the allowable Q points are only those intersections of the load line and the BJT output characteristic. No? So, dito, ano yung allowable nating Q points? Those would be this, and this. No? Because those are the only points that would satisfy both the Ohm's law relation of VCC, VCE, and IC, no, over RC, and the relation that is needed by IC and VCE across a BJT. No? Tapos, okay. So, if I label these A, B, and C, no? Alin dyan yung quiescent point na papasok ka na sa saturation? Alin dyan yung quiescent point na papasok ka na sa saturation? A, right? So there are quiescent points that would put the BJT in saturation, no? That are only allowed by the load line, right? So that's how the circuit, that's how we end up in saturation, no? Depending on our biasing. Kasi yung biasing natin, binabago niya yung V out, right? As we increase IB, no? 'Di ba? We know that increasing IB reduces V out, 'di ba? And we also know that increasing IB increases this, no? So, ang nangyayari when we increase IB is we travel from C to A and eventually we go into saturation, no? So that's what happens in the circuit. And also the reason why I am saying that saturation is only ever actually achieved, no? Kapag hindi na kaya nung outside circuit yung dinedeban natin sa kanya. That is, no? As it travels through the load line, it passes the VCE sat, no? So that's what happens in the that's why, no? That's why we get stuck in saturation after saturation. Imagine, no? If we increase IB any further, then we're going to push this a little bit over here. But notice that, no? This is going to be a little close, no? To where we started, no? I guess hindi siya ganun kadaling i-visualize when it comes to this graph. But as you get closer, no? So C kay B madali lang. Tapos B kay A madali lang. Kaso, when you're in saturation, you get stuck there, no? The more you increase IB, you don't really move anymore, no? So we get stuck near, well, in fact, actually, no, we're supposed to get stuck near 0.2, no? When we're choosing when we're moving our quiescent point, no? So anyway, that's how the BJT biasing works. Those are the rules of BJT biasing, no? And next, no, let's talk about what we consider.
We should be already planning for the new war and
Q point
a month. before the expiry of those.
Must have no high gain and no distortion. Itong distortion is what we talked about, no? We don't want, kasi, okay, dito sa taas, di ba? If C was a sinusoid, no? With this much amplitude, if the output was a sinusoid with that much amplitude, then ang mangyayari sa kanya, no, is magkikilip siya dun sa taas, di ba? And of course, that's known as distortion, no? So the distortion-free output is the is the smallest swing, or rather a swing, no, an output swing that allows for the largest um largest expected input size, no? Kasi of course, 'di ba, kapag maliit yung input mo, malaki yung output. Ay, kapag maliit yung input mo, then proportionally maliit yung output, no? Kasi they're related by A, no? Kaso kapag malaki yung input, then malaki din yung output with the possibility of distortion. 'Di ba? So then the no distortion factor in the consideration is the fact that we take into account the largest expected input, no? And make sure that the output of that will not be distorted. All right? Next consideration is the fact that this is impossible, no? Or rather, it's, well, actually, yes. Quite frankly, it is not so easy to do, no? So, essentially, we cannot simply place V in the base, no? So we need to think of more creative ways in order to place a V in that gets us in our desired quiescent point, no? Kasi ito is, it's ideal, no? It's an ideal voltage source. But you don't tend to be able to do this, no? It's not practical to do that. So what we want to do is we want to use a resistive network for biasing. And then 3, Q point must be stable versus component parameters. Though to be honest, this third point is not really too much of a consideration, though we will perform some calculations involving how much the Q point changes versus, say, beta and alpha of the transistor, no, or IS, no. So, well, one practical consideration where you're making actual circuits is the fact that you want it to be stable against component parameters, no? Like hindi kapag pinalitan mo yung 2N3904 with another 2N3904, no, which should be nearly the same, no? You don't want your circuit to break, right? So there are analyses that we could do in order to make it more stable against component parameters. So anyway, let's have an example, no? So an example of a bias circuit that we could do is simply this thing, no? So we have VCC and RC, no? We're used to those. Spoiler dun sa taas, no? And we also have an NPN BJT But let's place a base resistance here, no? We have RB done. All right? So now, we're going to have a DC bias, no? Dito sa circuit na to, right? So let's calculate. So if we assume, no? So our calculation will go like this, diba? So we're going to assume na naka-on yung transistor as we usually do, right? The first assumption is forward active. Second assumption is, first assumption forward active. Then we check if it's in saturation. If it is, then we then okay, then we reanalyze assuming that it's in saturation, no? Yun yung flow natin. So anyway, for this analysis, we're going to do VCC minus RB over 0 VCC minus 0.7 rather over RB would be your IB, diba? And your IC would be beta IB. But also, no, your IC is VCC minus VCE over RC. No? So we know IB and we know RC and VCC. So we can solve for the VCE of this circuit. No? So VCE would be RC. Sige, it's slowly isolated. No? So that's VCE is equal to VCC minus RC times beta IB. Diba? And since we know IB, we now have an expression for VCC, which is this. For VCE, no, or V out. Ayan. So this is your expression for VCE. All right? So with that, no, okay, no special values needed, no, other than, VBE on, we use VBE on here, no? But we got our quiescent point. We have we have an IC, no? Ano yung IC? We have beta VCC minus 0.7 over RB. So this is your IC. Well, IC is also this pala, no? But essentially IC is also this. That's your that's the equivalence of your load line, right?
Because I'm just checking. Because if you have like all of the hours
So this is load line, this output characteristic, no? So what else can we do, no, in these circuits? Well, an example design problem, no, that you could encounter in this circuit is when is the transistor saturated? Of course, kasi hindi natin sure kung saturated siya. We just have an expression for it, no? Where we assume forward active, right? So we need to check kung kailan magiging hindi na useful itong expression natin, no? And it's going to be saturated when VCE is equal to 0.2, no? Which would be equal to this thing, no? So then, it depends on what the problem is, right? So the problem could be stated as the maximum RC or the maximum RB or the maximum RC or the minimum RB, no? So we can solve this, no? We can solve this portion, like this, in order to find a biasing condition, no? Given VCC or given like one of these would be missing in that problem, right? And you want to make that decision. For example, no, VCC tends to be 5 volts because we can't really control what comes out of the battery. Beta is not controllable because that's part of your transistor and you're probably given only 1, 2, and 3904, no? Which is typically around, I don't know, 150, diba? So then your design choices are RC and RB, no? So you have to make sure that the choices of RC and RB will not put your transistor out of forward active, no? So this thing must be greater than 0.2, di ba? Yun yung saturation condition natin, no? So these are example problems of what you could encounter for biasing, di ba? Now, let's talk about varying, no? Um, sige. Let's talk about changing this circuit slightly, no? So, well, we're not actually changing it, no? We're deciding on the values. But let's analyze the effects, no, of changes in the values on the circuit itself, no? So we had the load line analysis earlier, di ba? Meron tayong mga ganito, right? Yeah. Tapos, we had this load line. Ayan, taas natin. Actually, I made the graph way too big. Sige lang nga. Well, medyo wobbly yung load line natin, but that's fine. No? So, ang load line natin dito, let's think about it. No? If this is the output characteristic, no, which puts that at IC and puts this at VCE, no? At VCE equals 0, then IC would be VCC over RC, no? That's 1. And then at VCE equals, well, okay, at IC equals 0, VCE equals VCC. Di ba? Kasi walang current dito, so VCC equals VCE. Di ba? Right. So then, no? Ito yung mga quote-unquote legal points para dun sa circuit natin to be in, no? And in fact, what allows us, no, to travel from one of these points to another point is, okay, so I'd like you guys to guess, no? This is, no, when we increase this, no, as we travel from this graph to this graph to this graph, di ba? We jump through those, right? Ano yung binabago natin dun sa circuit? Well, one consideration, right? One consideration is that um, IB increases, no? In each of these steps, right? When we step that up, we step up IB. Bakit? Kasi IB is beta IC in forward active, right? Well, this is how this graph was introduced to begin with, right? Is that these are level curves of IB, di ba? For each IB, tumataas to. exponentially to beta, right? Or proportionally to beta. So to increase IB, what do we do to a controllable factor in this circuit? Well, to increase IB, no, which is VCC minus 0.7 over RB, no? To increase IB, what I need to do is to decrease RB, di ba? No? So, we find that as RB goes down, we actually travel diagonally along the load line. And note that hindi siya binabago nung load line. Hindi niya binabago yung load line. It just changes the quiescent point at which we are along the load line. Ang binabago niya kasi is yung biasing nung BJT. Ang binabago niya is yung curve nung IC versus VCE nung BJT. Kasi binabago niya si IB. But it doesn't affect the load line. Because the load line only depends on these guys. Diba? So that's varying RB. Next is varying RC. No? Yun lang naman yung dalawang kaya nating baguhin dun sa circuit. No? Mostly. No? I mean, sometimes you have, pwede kang magpili ng transistor. No? But it's a nightmare in lab. No? Actually, when you have like a lab class where you need to design amplifiers with BJTs, no, as this class used to have, I don't recommend changing the transistor. Change everything but the transistor because it's very hard to choose a transistor kasi hindi mo naman nakikita from outside kung ano yung value ng beta and such, right? And of course, lahat naman yan 2N3904. Alright. So, kapag binago natin yung RC, yung, kapag binago natin yung RC, tama? Let's move on to dito. Okay. So, when we move to here, ang nangyayari when we vary RC, if you remember, is VCC over RC itong nasa taas. Tapos, VCC itong nasa baba nung load line. Diba? So, when we vary RC, we don't really affect the biasing of the BJT, or we don't really affect the output characteristic of the BJT because that's decided by RB. But, note na, ang binabago natin is ito. No? Nagbabago yung load line natin as we increase or decrease. Decrease, no? As RC decreases, our load line goes like that. No? And I hope that makes sense. Kasi VCC over RC itong point na to. No? So then we put VCC over IC higher when we decrease RC. Diba? In this circuit. And in this circuit, no? As RC goes up, no? We shift the load line like that. And so, no? We can probably, well, okay. What's the practical reason bakit natin titingnan to? Well, if you want to get out of saturation, you figure out, okay, apparently if I increase RC, I can get out of saturation. No? So yun lang naman yung nakita natin dito. It's a really nice thing to be able to do, right? Is that for a constant VCC, you know that you can just decrease RC in order to get out of saturation. No? Likewise, kanina, we saw that if we increase RB, we can also get out of saturation, diba? So that's one thing about that's another interesting thing about this um circuit, no? Now, well, of course, lastly, no, let's talk about varying VCC, no? So we can vary VCC in this circuit. All that it's gonna do, really, is ito, no? If we vary VCC, then tataas to, and tataas din to, proportionately, di ba? So, mag-shift pa ganun yung load line natin if we vary VCC, di ba? So, when we vary VCC, we find that for the same RC and RB, right? Hindi natin binago si RC, RP, no? Si VCC lang yung binago natin dito. Nag-shift pa ganun yung load line natin, and we end up also getting out of saturation, no? In forward active, no? Punta tayo sa forward active na ito. But, on the other hand, no? For low power designs, di ba? Gusto natin ibaba si VCC. And the problem is, di ba? If we increase VCC, we go up like that, no? But if we put VCC lower, then we go down like that. And it's very easy to fall into saturation kapag binaba natin si VCC, no? Kasi mas mababa yung capability essentially circuit to support the forward active current, di ba? So that's the trade-off, no? The circuits are actually very sensitive to VCC, no? So VCC, increasing it increases the power consumption of the circuit, so we don't like that. But decreasing it, while it lowers the power consumption, it really puts you into saturation most of the time, di ba? So yun lang naman. Lastly, no? Um, how do we put the input into this circuit? Kasi di ba ito yung circuit natin, no? So meron tayong V out, di ba? The entire V out, no? So ito yung V, small v, capital O natin, no? Saan yung V in, no? Or rather, the small v, small in. Kasi yung small signal na lang ang gusto natin kasi meron na tayong large V, large in dito, di ba? Or, well, yeah, meron na tayong large V, large in, which is equal to VCC here, no? So, paano natin ipapasok si V in? Well, you put in a capacitor. That's the easiest way to do it, no? With the presence of the capacitor, hindi na maapektuhan yung DC analysis mo, right? The capacitor will prevent the input, no, from like okay, the input could be from I don't know, SIGGEN, no? Ano bang pwedeng gawin ni SIGGEN? SIGGEN could screw this up big time. Kasi ang SIGGEN is parang 50 ohms yung output resistance niyan, di ba? So it could screw this circuit up big time, di ba? Would also give a path to ground kasi. Anyway, ayan, no? So the way that we couple V in, no, the small signal input into a circuit like this is by putting in a capacitor, no? And in fact, when I did the undergrad project in this, no, this was what most students did, and the lab handlers they didn't really have any problem with it because it is a good way, no, to couple the circuit, no. So you just put a capacitor there. It just has consequences in terms of frequency response. Yun lang naman siya. But frequency response is something that we're going to be talking about much later on pa naman, around the end of the set, which is not that far naman na, I think, pala. So, with that, no, let's talk about amplifiers. So the basic BJT amplifiers. By the way, let me confirm, no? You guys can still hear me. My internet connection is apparently unstable. Right. Sige, I'll send the attendance here on Discord na, and then I'll also send the um I'll also send the attendance over Discord. Hindi ko pala na-delete yung attendance last time, but you guys just note na may date yung yung pagka yung whenever you fill it up, may date yung pag-fill up, no? So don't be very late on it kasi even if I don't delete it, yung pag-sum up ko ng attendances, may script ako for that. Also takes into account kung kailan nyo fill up, no? So dapat within the day. Anyway, those are the attendance forms for today. Sige. So, BJT amplifiers, no? We have three configurations. We have sige, this one right here, no, that we've been talking about all along, no? Where this is your V in and this is your V out. It's called common emitter. So, paano mo malalaman kapag common emitter yung configuration ng BJT? Well, kapag yung ground nasa emitter, that's common emitter. No? Yun lang naman talaga. That's really all it is. No? Why is it called common? Because the emitter is common to both the input and the output in this topology. Essentially. Yun naman yung sinasabi natin dito. Now, the next configuration is common base. Yan. So, in common base, no? How do you know that it's common base? Again, no? It is left as an exercise to the reader to know kung bakit natin tinawag na common base. Okay, never mind. Siret, di ba? Nasa ground yung base, right? The base is common to both the input and the output. Now, if we refer to the differential voltage, di ba? So, yun lang naman yung fact na common base siya. Next is common collector. So, you have V in, you have V out, no? And you're gonna say, okay, sige. So, again, no, I would ask you kung bakit common collector ang tawag dito, and I'd ask you if you'd bet your life on it, and that would be dangerous, no? Because this is not in ground, no? This one is connected to VCC. The collector is connected to VCC, no? So paano naging common 'yon? Well, common collector essentially yung pagka-common nitong mga to is what we consider common is either VCC or ground, no? Because both of those are considered ground in small signal, right? Kasi DC voltage to si VCC, di ba? Wala siyang small signal, wala siyang small signal anything whatsoever, di ba? So when we do small signal analysis, which the amplifiers are, no, in small signal form, then mawawala din to. No? So essentially, in small signal, ground yan. No? So that's why in common collector, ground siya. So common ground pa din doon sa V in and V out yung collector. No? In the common collector configuration. No? Alright? Now, sige, back to all of the types. No? So these are all of the types. Yan. Now let's talk about why we would prefer some types over the other types. No? The common emitter is actually the topology with the highest gain. That's why we keep talking about it. And most of the problems that you will ever see is common emitter. No? Because we get the highest gain in common emitter. No? Um, common collector has the lowest output resistance. Which means that siya yung pinopront mo sa lahat ng output. No? Kasi, kung mababa yung output resistance niya, say 50 ohms, then makukuha nung load mo most of the output voltage, right? Kasi kung ito yung output voltage mo, magkakaroon ka ng voltage divider and it will go to the resistor with the highest resistance, di ba? So then for your output stages, you would always want a low output resistance. So then the last stage of your multi-stage amplifier, if ever, would be always common collector. No, that's why we like it. So ano si common base? But to be honest, I don't use common base, no, and I've never seen it used in particular. But if I remember correctly, no, it can be used as an input stage where the input resistance is actually extremely high. No? So yun lang naman yung um, uh, common base. No? But more commonly kasi ginagamit natin yung ano, di ba? Yung capacitor and also the fact that ideal yung signal generators natin for our projects, which means na mababa na din naman yung output resistance ng mga yon relative to the possible input resistance of these guys. No? By the way, this is for NPN configurations. No? So the slides contain PNP configurations. You can go look at that yourself. No? Sige. So, let's do some preliminary analysis, no, of a common emitter amplifier, no? This is your common emitter amplifier. We're not going to be talking about gain yet because I think that's next modules pa. I think. So, we'll do that in a bit pa. But, let's talk about yung transfer characteristic, no? Na sinabi natin kanina. Ano yung transfer characteristic? Diba pag ganito, yung, yung sinabi nating itsura niya. In reality, no, it doesn't actually look like this. No? So, this is right. No, this is your transfer characteristic. Diba? So, I dare say, no, that this is not what it actually looks like. It actually looks somewhat different, no? And let's derive the equations to actually get such a thing. So this V out versus V in, diba? So for a common emitter amplifier, we can get V out, no, as a function of VCC, RC, and the DC bias V in, diba? That's quite frankly, this is going to just be, tingnan natin. So V out is equal to VCC minus RC times IC, no? Which would then turn into, kung hindi natin gagamitin yung 0.7 assumption, which we're not going to use here, no? Bakit? Kasi Vin is directly connected to that, no? So masyado siyang magiging sensitive to Vin, no? We cannot assume that Vin is 0.7, of course. So what we're going to do, no, is multiply RC with the exponential equation for the BJT, no, which is this thing, VBE over VT minus 1, and voila, no, that's our equation for V out, no, versus the VBE, which is just V in, capital V, capital A. Yan. So this is our equation. Tapos, okay, can anyone identify, no, what assumption we had for this? The assumption is forward active. No? Kailangan forward active para magamit natin tong exponential equation na to, di ba? So anyway, this thing models what this part looks like. Diba? Kasi cut off to, FA to, saturation to, di ba? So this equation turns into that thing, no? And this is not a line, right? It's not a line. It's exponential. Diba? It is of the form something minus something e to the V in over VT. Diba? So in essence, no, what actually happens here is not a straight line, but an exponential. No? Pag ano siya, you know, pag ganun siya. And if you don't believe me, sabi ni Sir Chicho, believe Lawrence, kasi ginawa na ni Sir Chicho yung curve na to. No? So it does look like that. Diba? And let's look more into what goes into the curve. Diba? So, as we get closer to 0.7, of course, cut off yung transistor most of the time. And then it slowly starts turning on as it nears 0.7. Diba? So this is your VTC. No? And it kind of makes sense that it hovers around this range. Diba? Why does it make sense that it hovers around this range? Because VBE ito, di ba? Eh, depende sa value ni VBE, exponential yung current. So, mabilis siya magbago. Kaya ito yung range of voltages na meron tayo. Now, sige, enough of the picture, no? Let's just place the values here, no? So, this is around 0.7, babagsak na siya to saturation. All right. So, now, in terms of quiescent point considerations, no? Again, this A, this is B. If I told you guys to design something with a high gain, a common emitter with a high gain, which quiescent point would you choose, A or B? All right. So, the correct answer is actually B. No? So, thanks, Royce. We choose B for higher gain kasi mas steep yung slope, no? But typically, we would choose A, no? So if we were designing for high gain, we choose B. But typically, we choose to have high swing, right? Kasi kahit mataas yung gain ni B, kung sobrang lapit naman nyo dun sa output, then hindi rin ganun kalaki yung lalabas na signal from it, right? Which means we tend to choose A, right? So if we were to design a high swing amplifier, we're going to choose A. And most of the times we do choose A. No? So if I told you guys no to design it with the maximum output swing, then you guys should choose A. Right? And note na dito sa slope dito sa function na to, the slope gets steeper. No, it doesn't stop getting steeper until it actually hits saturation. No, so you can infinitely, like, not infinitely. No, you can get a maximum gain right at the edge of saturation. But the problem with that is, no, so edge of saturation. C has the highest gain possible, but you never want to bias yourself at C. Kasi hindi nagagalaw yung output mo. Ang output mo dyan, kalahati lang. Di ba? So that's not good, right? Anyway, that's it for the common emitter characteristic. No? So essentially, no? How do we determine the gain then? Right? Well, the gain is the slope of this curve, di ba? The gain is the slope of that curve, as we talked about. So then, the gain is the derivative of V out over V in, no? This is the gain. So then let's calculate the gain, no? Versus V in. But if V out is this equation, then all we have to do is take the derivative of this equation with respect to V in, and we're gonna get negative RC IS over VT e to the V in over VT. O, di ba? Calculus. Calculus, easy. Mas madali pa siya sa algebra, quite frankly. So, this is the equation of your gain. Di ba? And you find that, as I said, no? Yung gain, ang itsura mo ganyan. So your gain actually increases in magnitude. No, magnitude, we don't care about the sign of the gain. Of course, binabaliktad lang niya yung signal. So this is your gain, no? And from Sir Chicho's sheet, no, the gain actually reaches 400. No, that's insane. But at 400 gain, kalahati lang yung signal na lumalabas, no? And quiescent point A has a gain of around 200 already, no? Which is like pretty good, di ba? So yun lang siya. This is your gain versus V in. This is 0.7. This is like 0.6. No? So the optimal point is like just about 0.65. No? So this is the equation for the gain. But no, the thing to remember, no, because I myself never memorized this. The thing to remember is that the gain is the slope of the transfer characteristic. No, to get the transfer characteristic, we did circuit analysis. No, and then we took the derivative of the transfer characteristic and we found this. No, I don't have this equation memorized by heart. All this is just the derivative of something I know from circuit analysis. No? So this may look weird, and to me, it does actually look weirder than some equations because it's not quite so familiar with me. But we do get the gain from here. No? Sige. So, let's talk about the common collector amplifier next. No? right? So, for the common collector amplifier, sige, let's solve for V out. Now, V out is equal to, um, sige. Well, first, let's talk about IC, no? IC is equal to V in minus V out. Well, IS e to the V in minus V out over VT minus 1. So that's what IC would be, no? Let's call that RE for the resistor at the emitter, no? And if we flip this equation around, though, um, we can solve for we can solve for V in minus V out in terms of IC, no? So we have um, IC over IS plus 1 VT VTLN, no? So we have VTLN IC over IS plus 1 equals V out minus V in, no? But we can also flip this around, no? So we will have an equation relating V out and V in, no? So then we can express V out as VT, well, V in rather as VT, V out, yes, tama, V out as V in minus VT ln IC over IS plus 1. But we don't know IC, no? What we can do is V out over RE, no? Which is IE times alpha, no? So, wait lang. So let's say na IC muna to, no? And we know that IE is equal to alpha IC. Alpha IE is equal to IC. Bakit naging V in minus V out yung VBE sa equation? Because this is your VBE, no? So V in minus V out is VBE, right? That's where we get it from, no? So actually in the slides, VBE nga yung ginamit niya, hindi V out minus V in minus V out, but I went straight ahead, no? Sige, you guys can leave the meeting early. It's recorded naman, no? Sige. So, this is alpha IE equals IC, but this could also be, no? V out over RE plus, nasaglit na,
About your dancing concept.
So, apparently, yung simplification na ginawa natin dun sa calculation dun sa slides is alpha IE is approximately IC, no? So we can just straight up replace IE here with that, no? Which gives us
On the next steps for
V out over RE plus IS over IS, no? Or rather, V out over RE IS plus 1, no? And doesn't matter, no? So ito lang yung transfer curve natin, no? That's really all we need, no? It's a function of V out, relating V out and V in. Though the problem is, dalawang beses lumabas si V out, no? So as was hotly discussed in Piazza, and also here, no, I'll say it again, when your equation looks like this, of course, may curve pa din siya. But for each point, you're gonna have to do some equal spamming or shift solve in order to get things, no? Luckily for us, ginawa na siya ni Sir Chicho, and he found na ganito yung transfer characteristic. No? So, what's the what do we take away from the transfer characteristic na nakuha ni Sir Chicho? One, no?
For telco, we have shared the discount.
Ang laki ng range na valid siya. It's quite hard to get this thing out of saturation. Out of forward active, no? It becomes forward active a very long time. Itong common collector. Also, the gain is low. No? Actually, the gain is not just low. Can someone tell me, like, eyeball, no? Ano yung gain? Last na to, ano yung gain nung circuit na to? One. It's close to one. No? So actually, another name for a common collector, no? The other name for common collector is called an emitter follower. No? And let's see why. No? So, last na talaga. Truly, truly last. No? Ang ginagawa kasi netong circuit na to, no? Is, di ba, kung forward active, ito all of the time, no? As we observed it as. And this thing is 0.7 almost all of the time, right? It never leaves that area in forward active, diba? It's always close to 0.7. Then V in is always just V out plus 0.7. No? This is, so in this circuit, all it does really is transfer V in to V out. But the thing is, the output resistance is now this thing. But okay, is this thing parallel this thing? No? So we're gonna talk about this other thing later on. No? But we changed the output resistance from here to the new output resistance, but we did nothing to change the small signal voltage. No? Ito yung DC voltage. But essentially, V out just follows what V in does. No, they're just different by 0.7 in DC, which we don't really care about. No? So with that, ends our lesson for today. Next week, let's talk about common base, and then also the next, probably the next module. No, so wait for announcements with that. I'll also put for some announcements about whether or not we're going to be face to face on Wednesday, no, because there's a possibility that we might not. Other than that, I'll see you guys next week Wednesday, no, whether it be Zoom or in person.
Thank you po, sir.
All right.